So we left off last time with looking at Ohm's law. V is equal to IR, and we updated it for our AC work so that V is equal to the impedance times the current. You see there we have the phasor voltage V is equal to the impedance times the phasor current I. The impedance being a complex number, and we'll talk a little more about that. I've also noted up there at the top of the page that J takes on a lot of different names, square root of -1, 1e to the J90. We saw that with Euler's equations last time. Also, if you look on the complex plane, 1 at 90 is a valid way of expressing it. And then summarizing what we learned last time, I don't know that you need to copy this down, but going back to your notes from last time, we saw for a resistor that the impedance was equal to R. The impedance for a resistor is just the real portion, that's R, and that the current and the voltage are in phase. So tomorrow or later on in the week in laboratory, if you end up with an element and it produces current and voltage that's in phase, you'll say it's acting like a resistor. Then moving on to the inductor, we find that the impedance is j omega L. It's frequency sensitive. It's a function of frequency. As the frequency changes, the impedance is going to change. And we saw that the voltage leads the current, that V leads I, ideally by 90 degrees, but then we said a lot of inductors, instead of just being inductance, they had an awful lot of resistance. So usually it's not going to be 90 degrees in lab. You'll probably find that it's maybe closer to 30 degrees, significantly different than 90. But the voltage will always lead the current, and that is, of course, our Eli, E, the voltage leading the current. And then the capacitor, we saw that the impedance was 1 over j omega c, and we usually write that as minus j, then in the numerator divided by omega c. Again, it's frequency sensitive. As the frequency changes, it changes. And we saw that current leads the voltage. So it's really easy to determine whether you have an inductor or whether you have a capacitor by whether the current is leading the voltage or the voltage is leading the current. That, of course, leads us to our expression ice for Eli the Iceman. So that was our conclusion from last time. We did some examples. Hopefully you got a chance to try and practice this with your calculator. We don't want to turn this into a calculator class because everyone probably has a different calculator. A lot of people have a different calculator. But you want to be able to do this on the calculator too. So I'd like to talk a little bit more about the impedance Z beyond what we found out last time. Just quantify a few things. It has units of ohms. So make sure we're clear on that. We give the Greek symbol omega to. It is a complex number. Okay. We give it the same notation with that phasor dot, but it is technically not a phasor. It's a complex number. And we could write it a couple different ways. We could say that the impedance Z is equal to the resistance plus J. Sometimes we'll put X here, where we say that this is the resistive portion. And where we say that the complex or the imaginary portion is the reactive portion. There'll probably be a lot more memorizing of terms in this class than in the past. A lot of times people will talk about a reactive portion. We're expected to know that would be the complex or the imaginary portion. Of course, the resistive portion is pretty straightforward. You could also, if you wanted to, express this then in magnitude angle form. So it's going to have some magnitude. I won't put the phasor on it to indicate the magnitude. And it'll have some theta z, the angle of the impedance. So you can express it a couple different ways, and we'll see that in our lab calculations in a little bit. I think that pretty well deals with this. Of course, we can go up and relate it to this Ohm's law equation, where the impedance Z is equal to the phasor voltage divided by the phasor current. So we'll get that. One other thing is, before we leave this subject, we want to probably talk about admittance, and admittance is equal to the opposite, or the inverse, I should probably say. The admittance Y, so we give the admittance the symbol Y, is equal to 1 over the impedance. So before we had calculators that were really quick at flipping things, there's probably had some value in dealing with admittance when we did calculations. Now it's so easy to invert things. We don't see this a lot, although the concepts are still there, and we should probably be able to talk about them. If the impedance is equal to V over I, then the admittance, of course, would be equal to I divided by V. The admittance is, again, a complex number, and we'll indicate it with a phasor dot. we could break this up and say that the admittance Y is equal to the conductance, G, we'll give the symbol, we saw that last term, plus J, and then there's the complex portion or the imaginary portion, the susceptance. So we have the conductance, which is of course the inverse of the resistance, and then we have the inverse of the reactive portion, which is the susceptance. Okay, and the units on this are Siemens, which would be 1 over ohms. So maybe I'll write this over here, 1 over an ohm, which is actually sometimes we give it the upside down omega symbol. Okay. Like I said, we don't use this, so maybe in some derivations we'll use it, but probably the most important part is if someone comes along and starts talking about a susceptance term, what in the world are they talking about? Well, they're talking about the inverse of the reactive portion. If they're talking about the conductance, what are they talking about? They're talking about the inverse of the resistive portion. So these two terms here are probably the most important thing we've talked about there.
The 1 over ohm is just upside down ohm.
Yeah, horseshoe upside down. That's either one. Could be the admittance too. Other questions? Okay, so just filling in a few blanks from what we did last time. I'd like to look at what we're going to do in the lab this week then, laboratory number 1. Remember, that's the one where you have the formal report. So you want to be prepared not only with your safety glasses, but you probably want to bring a camera. Most people are packing around a phone with a camera, so it probably doesn't take any advanced preparation. But a picture is worth 1,000 words. So you probably want to take some pictures of your circuit so you can put those in your lab report. Also, I don't think anyone wants to do sketches of the oscilloscope face, so if you click off a quick picture of that, you can put that into your report too, because we're going to be using the oscilloscope to measure this. So I would bring a camera. If you don't have a camera, that's fine. You can make those traces and put them into your report, that's fine. But most people are probably running around with a camera. You don't come in and ask me to sign a piece of paper that you need some $600 iPhone to pass the class. So. Okay, so with laboratory number 1, you're going to set up this circuit. You're going to have some source here, and you're going to have some unknown impedance. I'll just say Z with a question mark here. And we're going to put that in series with the resistance, and we'll hope that it's close to 100 ohms. It really doesn't matter whether it's 100 ohms or 95 ohms, as long as we know what the value is accurately. And then we're going to talk about this current here. So we'll put the 2 channels of the oscilloscope. We'll put channel 1 probably across this whole thing. So channel 1 is going to go from this ground here up to this point here. And channel 2 will then go from ground up to that point there. So if we want to talk about the voltage across that impedance, that would be the difference between channel 1 and 2. We would take channel 1 and we would subtract channel 2. Likewise, if I want to talk about this current, that is the current through the resistor, what would that be? That would be the voltage that channel 2 is measuring divided by the resistance, right? Isn't voltage divided by resistance equal to current? Yeah, even in the phasor world, that works out. So channel 1, that'll be you're going to have a oscilloscope trace that probably looks something like this, and it's probably most convenient to measure from peak to peak. Whereas we want amplitude, so if you want the amplitude and you've got peak to peak, you're probably going to take half of the peak to peak value. So whatever wave is showing up for channel 1, you'll take half of the peak to peak value. And then whatever the phase shift is, when you compare this to the other wave that's going on there, there's going to be some phase shift here. That's going to be your theta. Okay. Now as far as 2 goes, I would still take half of the peak to peak value. But I would take it at 0. Why not make life easy for yourself and reference one of them to be 0? Yeah, I mean, you could put your 0 point at any place. You could put it there or there. I guess you could put it over here and make them both some odd angle. But why not pick one of them as 0 and then the other one is just shifted that much? So I'm going to take my channel 2 as my 0 reference. Then if I want the current, what I'm going to do is I'm going to take that voltage that channel 2 is giving me at 0 and divide by 100. So now that I have the current, I'll take the difference in voltage here that we said was the difference between channel 1 and channel 2, and if I divide by that current, I'll get the impedance. Okay. So like I mentioned, when we get into lab, and this is why you want to be there on time, I'll have this thing set up for one of the elements. You've got 4 different elements. You have a resistor, you have an inductor, you have a capacitor, and then you have a capacitor with a resistor. So I'll have it set up probably for the inductor, and we'll go through this. We'll take the data, just like you'll take the data, then I'll step to the board and go through these calculations. So hopefully it'll mean a little bit more when we're down there, but these are the calculations that we're going to do. And when we get done calculating this impedance, we'll probably have some magnitude and some angle, which may not mean a lot, but if I convert that, remember if you're on the complex plane, and you have some magnitude and angle, so there's your magnitude, there's your angle. You could convert that into some real portion and some imaginary portion, right? And the real portion is your resistance, and the imaginary portion is either going to be omega L, or minus 1 over omega C, or maybe R. And if you then come up with omega L equal a certain value, you could solve for L, right? Hopefully that matches the L, the inductor that you put in there. That's what the task is here. If you put a 1 Henry inductor in there and you come up with 0.997 Henries, how'd you do? You did pretty well, didn't you? Okay? So that's our goal on this, to see if we can make this measurement. The resistance, we'll be able to measure that on the inductor fairly easy. We just take the ohm meter to the inductor and we'll be able to come up with the resistance, and we'll find out that this number, at least for the inductor, is really quite large. So these are the calculations we're going to do. You may want to study that a little bit tonight, but like I said, I'll go through this again and put it up on the board in laboratory. Are there questions with this? Okay. Well, let's go do some examples so we get a little more comfortable with the calculations like we might get into at this point, how to deal with those phasors and complex numbers. So I've got some just good old-fashioned examples here. So I've got a problem here. It's expressed in phasor form. That is, we don't know what the inductors are, but rather the inductor is given as J2. If someone gives you the inductor in terms of henries, that would be specified in the time domain, but they're giving us in terms of J2, so they're giving us in the phasor domain. So that's good. We'll talk about how to convert from time domain to phasor domain eventually. So they've given this problem to us in phasor form, and we'd like to come up with Vs. Okay, this is the unknown, what the source voltage is there. They've given us this V1. That's actually a known entity. So let me come up with a game plan on this. Let me simplify this a little bit and say that I have some Vs here that's unknown, and we've got 2 ohms here, and then I could convert the rest of that into some impedance Z. Is that fair enough? Could I do that? I think I could get it reduced to that. And then I know that I have some voltage across here that's going to be V1. So by voltage division, could I not say that V1 is equal to the total voltage Vs times what? 2 ohms divided by 2 ohms plus whatever that impedance is? Does that work? Well, that's just good old-fashioned voltage division, isn't it? We don't want to forget the stuff we learned last term. I take the voltage across both of them, which is Vs. I multiply by the element that I'm trying to find the voltage across. That's V1, which is 2 ohms, and divide by the sum of the resistance, or in our case, the sum of the impedance. So I could rearrange this then and say that Vs is going to be equal to what? V1 times 2 ohms plus whatever that impedance turns out to be, divided by 2 ohms. Is that right? So now if I could figure out what that impedance is, it should be pretty easy work to get that. Okay? Well, let's see if we can go through this. If I look here, what's the impedance of those? Maybe we'll call this Z sub A. What's that going to be? What's the relationship of the 2 ohm resistor and that J1 ohm inductor that I've got circled with the dotted line? They're in parallel, aren't they? How do we combine resistors? How do we combine impedances that are in parallel? Inverse of the sum of the inverses, or if there's just 2 of them, we could maybe a little easier go, you're absolutely right, the inverse of the sum of the inverses, but if there's just 2 of them, we go product over sum, right? So let me do product over sum, so I could say that ZA is equal to the product, so I've got 2 times J1 divided by the sum, 2 plus J1. Okay, that doesn't look so bad. That's ZA. And then if I want to combine this with this whole thing, maybe I'll call that ZB. ZB up there. Great, we got ZB. What's the relationship of that minus J1 ohm capacitor with ZA? Series. So we could say that ZB is equal to ZA plus a minus J1. Okay. Or you could have just subtracted J1, that's fine. Let's see, then we've got one more thing, don't we? This whole thing here, we can note that ZB is in parallel with what? The J2 ohm inductor? So again, I could do product over sum. I could say that the impedance that I'm looking for, Z, that was this one over here, is really just going to be product over sum. So I'll take ZB and multiply it by the J2 ohms and divide by the sum, which will be ZB plus J2 ohms. Okay. So that's kind of our roadmap. So let's see if I can get this. Going back here, ZA, what's that going to be equal to? Well, I mean, this you can just do normal math on this. I don't know what other kind of math there is. We'd have J2, right, divided by 2 plus J1. Now's when you probably want the help of a calculator. I don't think you should use a calculator as a crutch. I mean, if we're pressed on a desert island or something, we probably should be able to convert those both into rectangular form. Not both into rectangular, both into polar form. Magnitude and angle, divide the magnitude, subtract the angles. But I've done that enough, so I think I'll just go right to the calculator, and let's see what we get. Now, I don't want to turn this into a calculator class, because if we were going to do a calculator class, we'd all have the same calculator. That's not what this is about. But suffice to say, getting a right answer is part of this class. So grab your calculator, pull it out. If you can't make it work, holler out. Does anyone have such and such calculator? And you may have to go sit next to the other person and have them show you. So we won't do this on every problem. So if you're frustrated with this process, rest easy. We're only going to do this for a problem or two, and then it's expected you know how to run your calculator, and we'll be off and running. So let's see what we get here. Anyone got that? 0.8944 at an angle of 63.43. If you have something that looks wildly different, you may be in rectangular form, which is fine. Flip it into a polar form. Few people getting that? Let's try it differently. Anyone not getting that? Okay, what kind of calculator are you using? Okay. Who else is running a TI-84? The person in front of you here. Did you get it? Okay, I'm working on it.
You should, if we're dealing with these complex numbers, you want to go with polar form.
Sometimes polar, sometimes rectangular. I mean, we'd probably be better off doing rectangular on this because I'm going to come down and add a minus J1 to it. Probably if you're using a TI-84, you're going to have to treat it like a vector, I would suspect. You got it?
Yeah.
Okay. Okay. Good. So you're the TI-84 guru now. Great. Okay. Well, I'll go one more step here. So I'm going to take this Z sub A. So this will be equal to 0.8944 at an angle of 63.43. I'm going to subtract J1. Probably be nicer to have that answer in rectangular because then it'd be really easy to subtract J1, but I'm going to do it with my calculator, so it doesn't really matter. So we should come up with 0.4472 at an angle of minus 26.57. Anyone get that? Few people? So then when I plug that in down there, so let's see what we get now. Anyone getting that? If I put that in rectangular, let's see what I get. Couple answers there. Anyone getting those? So I think I've got just enough room to finish this up. I can figure out that my V sub S should be equal to V1, which we were given as 10 at 0. I could really write that as just 10, but I'll say it's 10 at 0, times 2 plus this number and I have to divide the whole thing by 2. what did it come up with for VS? So I think that's your VS. That's the number that I got. Anyone get that? You people? Great. Yep.
At the very end, when you put in 10 at the angle, how did you do that on your calculator?
It's 10 at the angle 0, right?
Or sorry,
Yeah. I just put it in as 10.
Okay.
Sometimes there are some calculators that are real finicky that if you start putting it, if you have one number in complex form, then everything has to be in complex form, so you may have to fool it by putting in 10 at an angle of 0. But my calculator, I can just put in 10. In fact, to tell you the truth, I looked at it and I didn't like pressing buttons, so I recognized that 10 at 0 divided by 2 is 5, so I just multiplied it by 5 as I went through the problem.
It does force you to do that, though, it will be 10 plus 10i.
Well, let's see, what are some names for 10 at an angle of 0? 10 would be an appropriate name. 10 plus J0 would be an appropriate name. Okay. Good question. If your numbers are, if you think you're putting in the numbers right and nothing's working out, make sure that you're in degrees and not radians. Okay. That can be a stumbling block. Make sure you got parentheses. The TI calculators really like to have lots of parentheses. And then just practice. Yes. This one down here? That's just converting this from rectangular, from a magnitude angle to rectangular. That is to say, if I have, yeah, I got some space here. So if I go to the real and the imaginary plane, here is real. Here's imaginary. And I said I had 0.485 at minus 14. So there is 0.4851 at minus 14 degrees. Minus 14 degrees right there. Okay. And what I did is I converted it to this. This one turned out to be 0.4706. This one turned out to be minus 0.1176. You can actually just do that with trig. You would sine and cosine. Take the 0.4851 times the cosine of 14, and that will give you that one. Take 0.4851 times the sine of 14, and you put a negative sign on it, and that'll get you that one. What? Okay, so just polar to rectangular conversion. Yes?
Is there any advantage using the polar form or the rectangular form when we're trying to put it in the page?
You know, if I know that I'm going to be doing some adding, then I like to usually have the rectangular form. If I know I'm going to be multiplying or dividing, I like the polar form.
Okay, so it's just easier math-wise.
Yeah. But then if I'm using the calculator, it doesn't seem to matter. Okay. A little bit like what, riding a bike versus driving a car. I mean, if you're on your bike, you got to kind of attack the hill right, don't you? Not too much at the bottom and tire yourself out. In the car, you just, hit the right pedal and go. So. Other questions? Everyone's getting those? Okay. Well, like I said, the video will be posted up. The scratch work will be posted up. So if you're not getting to this point, that's what you need to do. Okay. Let's try another example then. Let's try this one. Looks like we've got things in parallel, and I'd like to find the current I. So if I could combine all of this impedance here and talk about some Z value from that, I would be pretty easy. I would be equal to what? The voltage divided by the impedance, which we could say is 10 at 120 divided by whatever the impedance value is. So our task then is to find the impedance value, really, isn't it? So what's that going to be? I could do them two at a time and product over sum, or maybe this is a good application for just the inverse of the sum of the inverses. Or you could argue that, hey, this is a great time for admittance and do it with admittance, and that'd be fine. But I'll just do it like this. I'm going to have 1 over 2 plus 1 over J2 plus 1 over minus J1, and be real careful with that negative sign. That's easy to lose down there in the denominator, plus 1 over 4. So I'll figure out what the denominator is first before I invert it so you can have a little check on that. So I got the denominator is 0.9014 at 33.69. And when I invert that, which hopefully makes sense. I mean, 1 divided by 0.94 should be something a little larger than 1. Remember that this 1 really had a 0 angle up here, didn't it? So 0 subtract 33.69 should give us minus 33.69. So if I go up to this equation now, yes?
For all the things that are inside that circuit that are parallel, we got resistor, inductor, and capacitor. We treat them all the same?
We add them up all like they're resistors, yes.
Even though the capacitor has the different.
Yeah, because the capacitor, remember, the J is in the J omega C is in the denominator, so we've already flipped it. So the impedances, you treat impedances just like you would resistors or inductors. Good question. Other questions? Okay, so I, we said, was the voltage, which is 10 at 120 divided by, and I knew this was going to come up, so that's why I left this in a magnitude angle form, 1.109 at an angle of minus 33.69. So I mean, you could do that by hand, 10 divided by 1.109 and 120 minus a minus 33.69, but if you got your calculator, it's a little easier with that. So I got too many significant figures there on the angle, but I guess we'll be okay. Anyone get that answer? Let's see, if I were to go on to the real and the imaginary plane. So there's the real. Imaginary. Where's the voltage? 10 at 120. There's the voltage, isn't it? Where's the current? You got 9 at 153.7. So That's greater than 120, less than 180, so there is I. Like that. I got V, we got I. So let's say I is leading V. I is leading V. What's that? Ice. It's capacitive, isn't it? So even though we have resistors and inductors in there, it is predominantly capacitive. It appears to be overall capacitive. What would be another way of proving that to yourself? This negative sign in the impedance. You don't get a negative sign in the impedance unless you're capacitive. Is there a question over there?
Yeah.
Okay.
So that rule you talked about in the graph, when you come back to the complete real side, you're always traveling counterclockwise with your arrow. It's not just whichever.
The way I think about what's leading and lagging is I always approach this as if I'm going that way.
Okay.
What do I come to first? So beyond the answer here, I mean, this is a nice answer and a good test for your calculator skills, and that's important at this point. Beyond that, it's nice to look at the impedance. What's the impedance? Predominantly capacitive, isn't it? Okay, when we get into power, that's going to have implications. We're going to talk about a certain kind of power factor and whatnot, that I is leading V. If this is what we have going on down in lab, we'll be able to say, yeah, indeed it's capacitive, right? Okay. Yes?
So the effect of the whole circuit is capacitive.
The effect of the whole circuit is capacitive, yes. So there's enough capacitance in there, it appears to be canceling out the inductors. The resistors are just going along for the ride. Well, when we get together next time, we're going to go on to more complicated analysis. You'll notice that the examples that we've done today have had one element or one source in them. I shouldn't say one element, but one power source in them, which we get to use simple analysis techniques like current division and voltage division and things like that. We're going to spice it up a little bit. We're going to start to put multiple sources in, and from last term, you'll remember that means you need to go with better techniques. We're going to look at node and mesh analysis. What's the implication for that with complex numbers? Well, now you have systems of complex numbers, so you're going to be asked to solve matrices of complex numbers. So that's your goal with your calculator, is to be able to solve a matrix, use maybe a row-reduced echelon form or something like that with complex numbers. So that's where we'll go next time. Take care till then.